Enceladus, Saturn's sixth largest moon, a tiny world orbiting a colossal planet nearly 900 million miles from the Sun. At just over 300 miles in diameter, it could fit comfortably within the borders of a single American state. And for much of astronomical history, it was considered little more than an unremarkable ball of ice, one frozen moon among dozens cluttering the Saturnian system. But don't let its seemingly unimpressive size fool you. When the Cassini space probe discovered enormous cryovolcanic plumes erupting from the moon's south pole, this little world brought the entire scientific community to a standstill. Nothing quite like it had ever been seen before. These weren't subtle geological whispers. They were dramatic fountains of ice crystals and vapor blasting hundreds of miles into space, visible even from a distance, cutting through the darkness like geysers on a cosmic scale. Scientists scrambled to understand what force could be powerful enough to drive such violent and sustained activity from such a small and seemingly frozen body. What was going on beneath that gleaming white surface? Flying directly through these icy jets gave us something remarkable, a chance to taste another world's interior without ever having to land on it. As Cassini made repeated passes through the plumes, its onboard instruments went to work, analyzing everything they encountered in extraordinary detail. The probe discovered water, not just frozen water ice, but evidence of liquid water. It also detected complex organic molecules, the carbon-based building blocks that form the chemical foundation of life as we know it. And woven through all of this was something even more exciting. Strong hints of a hidden global ocean buried beneath the moon's icy shell, an ocean that appeared to be in contact with a rocky seafloor lined with hydrothermal vents, actively pumping heat and minerals into the water above. That combination, liquid water, organic chemistry, and hydrothermal energy, is almost exactly what scientists believe gave rise to life on early Earth. Suddenly, this obscure little moon had become one of the most scientifically compelling objects in the entire solar system. But in 2017, Cassini ran out of fuel. After 13 extraordinary years in orbit around Saturn, mission controllers made the deliberate decision to plunge the spacecraft into the planet's atmosphere, incinerating it to prevent any possibility of contaminating the moons below with earthly microbes. As it dived into Saturn's clouds and disintegrated, it took with it our only operational means of probing Enceladus up close, leaving us with a long and tantalizing list of unanswered questions that have haunted planetary scientists ever since. Does the ocean beneath the ice truly encircle the entire moon, or is it merely a regional body of water trapped beneath the South Polar region? What exactly is happening at the interface between that ocean and the rocky seafloor far below? How long has this environment been stable, and has it persisted long enough for biology to take hold? And most importantly, the question that now sits at the very heart of astrobiology: could Enceladus be home to life? A decade on, we have not yet returned to Enceladus in person, but the science most certainly has not stopped. New missions are in various stages of planning and proposal, each designed to do what Cassini could not: to linger, to sample more thoroughly, and to search with instruments purpose-built for the detection of life. In the meantime, the James Webb Space Telescope has turned its extraordinary infrared gaze toward the moon, peering at the plume system with a sensitivity that no previous observatory could match, revealing details about its composition and scale that continue to astonish researchers. And back on Earth, teams of scientists are still methodically mining the vast archive of data that Cassini sent back over its lifetime, applying newer analytical techniques and fresh theoretical frameworks to old measurements in ways that continue to yield surprising discoveries. And luckily, we've found more answers than you might think. Before we start, I want to tell you something. A lot of strange things have been happening in space lately, so subscribe to this channel right now and I'll tell you even more secrets of space. And write in the comments below what you think about all of this. At just 500 kilometers across, Enceladus is a remarkably tiny world, comparable in size to the state of Arizona. It traces its orbit 238,000 kilometers from Saturn at a distance so remote that the sun is reduced to little more than a distant cold spark in the sky. Surface temperatures average a bone-chilling minus 201 degrees Celsius, making it one of the most frigid environments in the entire solar system. All of these factors combined, its diminutive size, its extreme distance, its punishing cold, made Enceladus an incredibly difficult target to detect and track from Earth. It was finally discovered by Sir William Herschel in 1789, and coaxing it into view required the largest telescope the world had ever seen at that time. The instrument was a monumental achievement in its own right, built by Herschel together with his remarkably gifted sister Caroline, who was herself a skilled astronomer and comet hunter. So ambitious was the design that its half-ton primary mirror demanded more than a year of painstaking, labor-intensive polishing before it was ready for use. The sheer scale of the undertaking was unprecedented. Yet, even through this behemoth of a scope, Enceladus revealed almost nothing of itself. It appeared as nothing more than a faint, unremarkable, icy point of light, indistinguishable from the countless other frozen fragments orbiting Saturn. Herschel's telescope was so far ahead of its time that it remained the definitive instrument for observing this Saturnian satellite, and his initial frustratingly featureless impression of it endured almost unchallenged for nearly 200 years. For 2 centuries, Enceladus was essentially an astronomical footnote, known to exist, but yielding none of its secrets. It wasn't until the 1980s, when the twin spacecraft Voyager 1 and Voyager 2 performed their swift, historic flybys of the outer solar system, that our perspective shifted forever. The images they sent back across hundreds of millions of kilometers of empty space did not show the battered, featureless world scientists had largely expected. Instead, they revealed something deeply puzzling. Regions of Enceladus' surface that were remarkably smooth and almost entirely free of impact craters. In planetary science, a lack of craters is a powerful signal. It means a surface is geologically young, recently reshaped by internal forces. This strongly suggested the moon had been seismically active in its relatively recent past. Even more curiously, Enceladus was found sitting directly within the densest region of Saturn's E-ring, a vast and diffuse band of icy particles encircling the planet. This was no coincidence, scientists suspected. The moon appeared to be actively feeding the ring with fresh material from somewhere within itself. The question that began to form, tentatively but irresistibly, was a profound one. Was Enceladus, against all odds, geologically alive? The mysteries raised by the Voyager flybys elevated Enceladus to a high-priority target for future exploration and directly fueled the ambitious planning of the Cassini-Huygens mission, a collaborative undertaking between NASA, the European Space Agency, and the Italian Space Agency. A Titan 4B rocket launched Cassini in 1997, sending it on a long, carefully choreographed journey through the inner solar system. In late 2004, nearly 6 years after a double slingshot gravitational maneuver around Venus that gave the spacecraft the velocity it needed, Cassini finally arrived at Saturn, ready to carry on and greatly deepen the legacy of the Voyager probes. It was a monumental scientific and engineering effort, one that would ultimately generate more than 4,000 peer-reviewed scientific papers across dozens of disciplines. But no single discovery generated more excitement, more urgency, or more profound implications than the events of early 2005. During Cassini's first close flybys of Enceladus, its cameras caught sight of something extraordinary. Massive geysers erupting from the moon's south polar region and blasting material directly into the vacuum of space. These weren't subtle geological whispers, they were dramatic, powerful plumes, ejecting an estimated 250 kilograms of water vapor and ice particles every single second, at speeds exceeding 1,000 kilometers per hour. The implications were immediate and staggering. This confirmed beyond any reasonable doubt that Enceladus possessed a dynamic atmosphere and vigorous, ongoing geological activity. Somewhere beneath that frozen crust, something extraordinary was happening. NASA immediately shifted the mission's priorities in response, ordering Cassini to perform what many considered a daring and unconventional maneuver, flying just 50 kilometers above the moon's surface to effectively taste the erupting plumes by flying directly through them and analyzing their chemical composition with its onboard instruments. It was a calculated risk, but the potential reward justified it entirely. What was worth such a risk? NASA was searching for signs of extraterrestrial life. The plumes, it turned out, contained water vapor, molecular hydrogen, silica nanoparticles, and complex organic compounds, precisely the kind of chemical cocktail that could, in principle, support microbial life as we understand it. Beneath the icy shell of this tiny frozen moon, there appeared to be a vast liquid water ocean, kept warm by hydrothermal activity on the seafloor below, an environment strikingly similar in some respects to the deep ocean hydrothermal vents on Earth, where life thrives in total darkness. The universe, it seemed, had hidden one of its most tantalizing possibilities inside a world smaller than Arizona, orbiting nearly 1.5 billion kilometers from the sun. A major motivator of our exploration of space is the hope that we are not alone in the universe. The possibility that life exists somewhere beyond Earth drives missions, inspires scientists, and captures the imagination of anyone who has ever looked up at the night sky and wondered. To define what we are even looking for out there, NASA describes life as a self-sustaining chemical system capable of Darwinian evolution. It is a deliberately broad definition, one designed to avoid being too Earth-centric, while still giving researchers something concrete to work with when they point their instruments at a distant world. But what does that definition actually mean when we are searching on a small, icy moon orbiting Saturn, hundreds of millions of miles from the nearest star? When it comes to Enceladus, scientists break the problem down into 4 fundamental boxes that need to be checked: liquid water, energy, the right chemicals, and enough time for life to potentially take hold. First up is liquid water, the universal solvent of life as we know it. Water is not merely a convenient habitat for life on Earth, it is the medium in which the chemistry of biology actually happens, the substance that allows molecules to meet, react, and build complexity. The question for Enceladus, though, is not simply whether liquid water exists there. That much has become abundantly clear from decades of observation. The deeper and more important questions are how much water there actually is and where precisely it is coming from. Cassini's initial photographs and infrared images from 2006 revealed something extraordinary. there was significant heat concentrated at the south pole of Enceladus. One of the most iconic images to come out of that mission shows what scientists came to call the tiger stripes, a set of long, dramatic fissures carved into the moon's icy crust, running roughly parallel to one another across the southern polar region. These fractures hinted powerfully at intense geological activity churning beneath the frozen surface. It became clear that some form of liquid ocean must exist below, possibly accompanied by hydrothermal activity vigorous enough to drive the enormous ice and water vapor plumes that erupt into space. For years, however, scientists assumed this ocean was relatively modest in scale, probably a small, lens-shaped body of water tucked beneath the South Polar region. That picture changed dramatically when researchers spent 7 years painstakingly tracking surface features across Enceladus. What they discovered was that the moon librates, meaning it wobbles slightly as it orbits Saturn, and it does so far more than would be physically possible if there were only a small polar ocean beneath the ice. A limited, localized body of water simply could not produce that much wobble. The implication was stunning. The rocky core of Enceladus is not rigidly connected to its icy outer shell the way you might expect. Instead, a global ocean of liquid water separates the two, wrapping entirely around the core and extending beneath the crust across the moon's entire surface. We are not talking about a puddle or a buried lake. We are talking about a world-encircling ocean hidden beneath miles of ice. Then, in 2025, came another significant breakthrough. Scientists from the University of Oxford, the Southwest Research Institute, and the Planetary Science Institute returned to archival Cassini data and compared observations of Enceladus's North Pole, taken during the moon's winter in 2005, with observations from its summer in 2015. What they found extended the story in a remarkable direction. Heat was not only escaping from the South Pole, as had long been known, but also from the North Pole. The northern polar region was running approximately 7 degrees Celsius warmer than theoretical models had predicted it should be. That might sound modest, but in the context of a frozen moon this far from the sun, it is a substantial and revealing discrepancy. The result tells us that Enceladus is generating considerably more internal heat than scientists had previously estimated, and it strongly suggests that the ocean beneath the ice may have been stable and persistent for a very long time, perhaps long enough for life to have had a genuine opportunity to emerge. But that raises an immediate and obvious problem. Enceladus is extraordinarily far from the sun. As noted earlier, the average surface temperature on this moon sits at around minus 201 degrees Celsius, a cold so profound and unforgiving that by any ordinary reckoning, liquid water simply should not exist there. The sun's warmth is far too feeble at that distance to account for it, so the next box on the scientists' checklist was energy. Something had to be generating all that internal heat, and the answer was not immediately obvious. One natural candidate was radioactive decay within the moon's rocky core, the same process that contributes to Earth's internal warmth. But when researchers ran the numbers, they found that radioactive decay alone could account for only around 1% of the heat that Cassini had actually measured pouring out of Enceladus. Something far more powerful had to be at work. So in 2017, a team led by Gaël Choblet proposed a compelling solution to explain how Enceladus maintains its remarkable subsurface ocean. Enceladus is tidally locked to Saturn, meaning the moon only ever shows one face to the planet, much like our own moon always presents the same side to Earth. This gravitational relationship distorts the shape of Enceladus as it orbits, stretching and squeezing the moon in a rhythmic cycle that creates heat deep inside through internal friction. And it is this process that powers the geological activity we observe. But generating heat alone is only part of the puzzle. It's not enough to just produce that energy and radiate it away into space. It needs to be physically transported from the rocky core up through the ocean above. How does that happen? Well, incredibly, it seems that liquid water actually perfuses the silicate mineral core itself, seeping deep into the rock where it is heated, and then rising in focused plumes that pepper the seafloor concentrated around the South Pole. Picture it like a slow, ancient circulation system buried beneath miles of ice and ocean, quietly churning away in the dark. In 2022, a study led by Wanying Khan found further proof of these hydrothermal vents. Working from Cassini's wealth of observational data, the team constructed detailed models of Enceladus's icy surface in an attempt to calculate the salinity of the ocean hidden beneath. What they found was striking. The ocean is just a little less salty than the seas we find here on Earth. That particular measurement matters enormously, because a salinity level in that range tells scientists that there must be, or have been at some point in the moon's history, significant water-rock reactions occurring at depth, which is essentially another way of saying vents. The chemistry of the water carries the fingerprint of its own history, and that fingerprint points unmistakably downward, toward a rocky, hydrothermally active seafloor. Hydrothermal vents are credited by scientists as one of the most plausible environments for powering the origin of life on Earth. These extraordinary structures, where superheated mineral-rich water surges out of cracks in the ocean floor, create steep chemical and thermal gradients that can drive complex chemistry and provide abundant energy for microorganisms to exploit. The possibility that such vents may also exist on a small moon orbiting a gas giant hundreds of millions of miles from the Sun is an electrifying discovery because they give us what we consider the third essential requirement for life, a sustained and diverse source of chemicals. Cassini was equipped with a mass spectrometer, a remarkably sensitive instrument capable of identifying individual molecules by measuring the precise mass of their ions. On its daring flybys through the plumes erupting from Enceladus' south pole, it detected hydrogen gas, believed to be a potential fuel source for early microbial life, in the same way it sustains certain microorganisms in Earth's deep-sea vents today. It also identified complicated hydrocarbons, organic compounds incorporating oxygen, carbon, and nitrogen, the kinds of molecules that begin to hint at the building blocks of something more complex. But scientists racing to process the enormous volume and richness of data flowing back from Cassini simply couldn't keep pace with what they had collected. Before researchers could work through it all, the Cassini mission itself came to an end. On the 15th of September 2017, the spacecraft was deliberately sent hurtling towards Saturn and was vaporized by the crushing pressure and heat of the planet's atmosphere. It was a self-destructive maneuver carried out by design, a final act of caution intended to protect potentially habitable environments on moons like Enceladus and Titan from any risk of contamination by Earth-borne microbes that might have hitched a ride on the probe. Even in its death, Cassini was acting as a guardian of the very life it had spent years searching for. Though Cassini's mission had been completed, ours had not. The data it left behind would continue to yield discoveries for years to come. An analysis in 2018 confirmed the existence of ring-shaped organic molecules, a significant step up in chemical complexity, along with simple oxygen-containing molecules, indicating that at least some limited but meaningful chemistry was actively occurring within the plume material ejected from the ocean below. Another huge boost to the search for life came in 2022, when the last element considered crucial to biology was finally identified in the data: phosphorus. This was no minor footnote. Phosphorus is fundamental to the architecture of life as we know it, forming the backbone of DNA and RNA and playing a central role in the energy transfer molecule ATP, which powers virtually every living cell on Earth. With its discovery, the checklist was complete. Scientists now had evidence for all 6 of the main chemical elements believed to be necessary for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, a set known collectively by the acronym CHNOPS. For a while, this felt like the end of the story. The boxes had been ticked, the evidence assembled, and Enceladus had emerged as perhaps the most compelling candidate for extraterrestrial life anywhere in the solar system. But it turns out, this particular book had a few more chapters still to go. When scientists first sat down with the mass spectrometer data returned from Cassini, they weren't entirely confident in what they were looking at. It turns out that the spectra of a carefully prepared sample, analyzed while stationary in a lab, looks somewhat different to the one obtained by crashing the detector into ejecta at 64,000 kilometers per hour in space. The conditions of collection matter enormously, and the differences in the resulting data are not trivial. A mass spectrum analyzer works by ionizing and breaking a molecule apart at high energy. Crucially, how the molecule breaks apart matters just as much as which molecule it is. A molecule's chemical fingerprint can look quite different depending on how it was fragmented, in the same way that a watermelon prepared with a knife looks entirely different from one prepared with a blender. Both methods give you watermelon, but the resulting picture is unrecognizable from one to the other. By understanding the typical pattern of how a particular substance breaks apart under specific conditions, the predictable pathways of fragmentation, scientists can work backwards with much greater confidence to determine what the original molecule actually was. Improved analytical tools and a deeper understanding of these fragmentation patterns helped a team, led by Nozer Khawaja from the Institute of Space Systems in Stuttgart, do exactly that, applying fresh eyes and more sophisticated techniques to data that had already yielded so much. After more than a decade of studying the plume flybys, Khawaja's team published their results, using samples that were collected during one of Cassini's most daring passes, just 20 kilometers from the moon's surface. That is extraordinarily close enough that the probe was essentially skimming the very source of the eruption. Unlike many of the other particles the probe collected during its years at Saturn, these samples were just minutes old at the time of collection, and therefore largely unchanged by the ionizing radiation streaming from the sun that gradually alters the chemistry of other particles drifting through the E-ring over longer timescales. These samples, then, were about as pristine as science could hope for, a remarkably direct window into what is actually present in the oceans of Enceladus, before the universe had a chance to interfere with the evidence. And what Khawaja's team found in those samples pushed the conversation about life on Enceladus to an entirely new level. In the most chemically rich examples, they identified molecules more closely related to the building blocks of biology than anything detected there before. carbon dioxide, carbon-rich alkanes and alkenes, cyclic esters and ethers, ethals, and a range of other nitrogen and oxygen-bearing compounds. Taken individually, none of these would raise an eyebrow in a chemistry lab. Taken together, in the context of an ocean world hundreds of millions of kilometers from Earth, they represent something remarkable: complex chemistry, potentially powered by hydrothermal vents on the ocean floor below. These molecules are sometimes described as the Lego blocks of chemistry, and the analogy is apt. Each functional group is a building block that can connect with others, enabling more elaborate and varied reactions. The more of these groups are present, the richer the chemistry that becomes possible. In a laboratory setting, given the right conditions, mixtures like these can generate reactions of such layered complexity that they begin to exhibit something that looks startlingly like Darwinian evolution: the preferential survival and replication of certain molecular arrangements over others. And once you have chemistry capable of evolution, there is really just one last ingredient required: time. That is the central question now hanging over Enceladus. What we need to know is how stable and how frequent this geothermal activity actually is. Has the moon been geologically active for long enough that life, if the chemistry is right, would have had a realistic opportunity to emerge and take hold? Millions of years? Billions? The difference is everything when it comes to the probability of biology getting started. Although Cassini spent 13 remarkable years in orbit around Saturn, gathering data that continues to be analyzed to this day, that timeframe was, of course, far too short to answer a question operating on geological and biological timescales. To get a broader view, literally, scientists turned to a far more powerful instrument. Enter the James Webb Space Telescope. A team led by Dr. Geronimo Villanueva used 10 hours of precious JWST observation time to check in on Enceladus, and what they saw stopped them in their tracks. The moon had an even more enormous plume erupting from its south pole than previously appreciated, expanding outward to roughly 20 times the diameter of the moon itself, significantly larger than anything Cassini had directly observed. This was not a minor upward revision. It fundamentally widened the known scale of Enceladus's activity, suggesting the moon is even more geologically vigorous than the decade of Cassini data had implied. And in doing so, these observations also solved another puzzle that had lingered for years. Where does Saturn's upper atmosphere get its water? The JWST images show that Enceladus continuously feeds a vast torus, a donut-shaped ring, of water ice particles encircling Saturn, making it the only moon in the entire solar system known to directly influence the atmospheric chemistry of its host planet. That is an extraordinary distinction. A small, icy moon, barely 500 kilometers across, actively shaping the chemistry of a gas giant many thousands of times its size. But the influence of these water ice particles does not stop there. As they travel outward through the Saturn system, they are stripped of electrons by the same radiation environment that Cassini worked so hard to account for in its mass spectrometry readings. This stripping process ionizes the particles, transforming them into an electrically charged plasma. And plasma, in the presence of a powerful magnetic field like Saturn's, does not simply drift passively. Scientists have recently discovered that this plasma interacts dynamically with the planet's magnetosphere, generating vast plasma waves known as Alphen wings, stretching an almost incomprehensible 504,000 kilometers in length. That is roughly 2,000 times the radius of Enceladus itself. The primary Alphen wing streams directly from the moon toward the planet along magnetic field lines, while secondary waves are reflected back outward, creating an intricate and beautiful lattice of plasma woven through the Saturn system. We still do not fully understand the behavior or implications of these structures, but they stand as a striking and unexpected consequence of Enceladus's great geysers, a reminder that what begins as liquid water forcing its way through cracks in an icy shell can ultimately send ripples, electrical and otherwise, across a system hundreds of thousands of kilometers wide. But none of this answers the most pressing question of all: how long will this activity last? Within the last year, decade-old data from the Cassini Composite Infrared Spectrometer was subjected to a rigorous new analysis, comparing its measurements against detailed models of Enceladus's surface temperature. The research team, comprising scientists Georgina Miles and Carly Howitt, were able to demonstrate something quite remarkable. The total thermal output detected across the moon's surface is very well matched with the predicted heat generation occurring deep within the core. This is not a trivial finding. It means the moon's internal engine is running at precisely the rate needed to sustain its subsurface ocean, and it suggests that Enceladus's current ocean epoch, this vast liquid window of geological time, will be long-lived. And that is exactly what life needs to emerge. Biological complexity does not arise overnight. It requires stable conditions, sustained chemistry, and time measured not in thousands but in millions or even billions of years. Enceladus, it seems, may have all of that on offer. It is incredible how much more has been learned simply from reanalyzing old Cassini data with new techniques. Modern computational tools, refined atmospheric models, and fresh scientific perspectives are unlocking secrets buried in observations that were made years or even decades ago, waiting patiently for the right questions to be asked of them. And it is not just the professionals who are making discoveries. Amateur astronomers and enthusiasts, armed with publicly available archival data and a keen eye, have also contributed meaningfully to our understanding of this distant moon. In 2017, amateur astronomer Ted Strike was doing exactly this kind of patient archival work when he looked back at old Voyager images of Enceladus and found something that had gone unnoticed for decades. A feature that could have dramatically changed the course of the original Cassini mission, a water plume. Faint, easily dismissed, but unmistakably there once you know what you were looking for. Can you spot it? The fact that it was hiding in plain sight for so long is a humbling reminder of how much can slip past even the most careful initial analysis, and how revisiting old data with new eyes can be just as scientifically valuable as gathering entirely new observations. If we had known about that plume when the Cassini mission was still in the planning stages, how different might the design of the spacecraft have been? Would the instruments have been optimized differently? Would the trajectory have been plotted to bring the probe through that geyser of material, sampling it directly for organic molecules and signs of biological chemistry? These are fascinating counterfactual questions, and they speak to how much the discovery of active geological and hydrological processes on Enceladus transformed our entire framework for thinking about ocean worlds. Whatever changes scientists and engineers might have made back then, they now have a genuine chance to realize a new and far more informed vision, as a new generation of missions is being planned to continue and expand upon the foundational work of Cassini. The European Space Agency is pushing forward ambitiously with a mission currently set to launch in 2042, designed to arrive at Saturn in 2053 and potentially achieve a landing on Enceladus itself as early as 2058. That would be a historic moment, the first time any human-built craft had touched down on a world with a confirmed subsurface liquid ocean and active geological venting. The scientific return from such a landing could be transformative. We already know Enceladus has all the conditions thought necessary to kickstart life: liquid water, chemical energy, organic compounds, and now evidence of long-term thermal stability. So it is genuinely exciting to ask the question that has been building through decades of remote observation and data analysis. What will we actually find when we look below the ice? The answer, whatever it turns out to be, will be one of the most significant discoveries in the history of science. Fortunately, we will not have to wait quite that long to get some meaningful answers on the broader question of life on icy moons. Another ESA mission called JUICE, the Jupiter Icy Moons Explorer, is already on its way through the solar system and is expected to arrive at Jupiter in 2031. Its targets are three of the gas giant's most intriguing moons: Callisto, Europa, and Ganymede, each of which harbors its own subsurface ocean beneath a frozen exterior. The mission's central purpose is to investigate the emergence of habitable worlds around gas giants, probing whether the conditions that make Enceladus so compelling are replicated or even exceeded elsewhere in the outer solar system. Two other proposed missions would explore Saturn's moons in entirely new ways, pushing the boundaries of what robotic exploration looks like. The Dragonfly mission to Titan is perhaps the most visually striking of all. It will take advantage of Titan's thick nitrogen atmosphere, dense enough to support powered flight, and deploy a drone-like rotorcraft for the very first time on a natural satellite beyond Earth. Skimming across Titan's alien landscape, sampling its complex organic chemistry from the air, Dragonfly represents a bold new chapter in how we reach out and touch the worlds around us. Outside of the national space agencies, a privately funded mission called Breakthrough Enceladus is also planned, though the project has been largely quiet in recent years and currently appears to be dormant, its ambitions perhaps waiting for the right moment or the right funding to reignite. But the mission that genuinely fills me with the most anticipation is the Enceladus Explorer, a project funded by the German Aerospace Center that proposes something almost science-fictional in its audacity. The plan is to send a nuclear-powered device called an ice mole, and yes, you heard that correctly, to literally melt its way deep into the icy crust of Enceladus. Rather than simply observing the moon from orbit or sampling what gets ejected into space, this probe would burrow downward through kilometers of ancient ice, exposing untouched niches and hidden microenvironments within the shell itself, places that have never been disturbed, never been contaminated by the vacuum of space, and potentially never been touched since the solar system first formed. It is hard to think of a more direct way to go looking for life. If any of these missions, whether orbital, flyby, or burrowing, return even the faintest hint that proto-life processes are active on a body sitting so far outside the conventional habitable zone, the implications would be staggering. We would have cracked open a whole new realm of possible locations where life could take hold, not just in our own solar system, but scattered across the galaxy in places we had previously written off as too cold, too dark, too distant from their stars. Icy moons are extraordinarily common around gas giants, and gas giants themselves are common throughout the universe. If life can thrive beneath the frozen shell of Enceladus, driven by tidal heating and chemical gradients rather than sunlight, then the census of potentially inhabited worlds multiplies dramatically. Maybe life isn't rare after all. Maybe we have simply been looking in too narrow a slice of the cosmic landscape. I am always reminded of a fantastic line from the physicist Jeremy England, who put it with wonderful simplicity. You start with a random clump of atoms, and if you shine a light on it for long enough, it should not be so surprising that you get a plant. The implication is profound, that life may not be some extraordinary accident, some vanishingly unlikely lottery win, but rather a natural and perhaps even inevitable consequence of energy flowing through matter over time. Chemistry, given the right conditions and sufficient patience, may tend toward complexity. Enceladus, with its warm liquid ocean churning beneath the ice and its chemistry actively in motion, may be exactly the kind of place where that tendency plays out. Perhaps scientists didn't see those plumes on the original Voyager images because they simply weren't expecting to see them. The data was there, the signal was present, but the mind filters for what it already believes to be possible. Now that we know what we're looking for, and now that our frameworks for where life might exist have been stretched and revised, there is no doubt that more discoveries are on the way. Some hiding in plain sight in archives we've already collected. There is almost certainly yet more to find within Cassini's extraordinary data, even now, more than a decade after its mission ended in spectacular style, diving deliberately into Saturn's atmosphere in a final act of controlled destruction designed to protect the very moons it had spent years revealing. The dataset it left behind is so rich, so dense with information, that researchers are still working through it, still finding surprises. And I am as genuinely excited now as I was back in 2004, when the probe first reached Saturn and its moons and began sending back those first breathtaking images of a system far stranger and more alive than anyone had dared to hope. That's all for today. If you like space stories and want to stay up to date with new episodes, subscribe to this channel and turn on notifications. See you in the next podcast.